So in this talk, we are going to show our more recent effort of sort of like leveraging fluctuations in the 2D limit to realize a new phase of matter in the 2D. And this state is the so-called 2D vestigial nematic state that was induced by spin fluctuation in a honeycomb XY magnet. Okay, let me start by saying that 2D magnetism in van der Waals system was discovered in 2016 to 2017-ish. So over the past decade-ish of time, we gradually realized two very unique aspects about 2D magnetism. One is really due to the reduced dimensionality, we have stronger spin fluctuation effect. And the other is because, like the last speaker was saying, that we have this kind of layered structure so that we can do twist engineering to even engineer the spin Hamiltonian of a system. So then in the first aspect, there are actually two routes people are trying to go towards. So one is to really fight against this fluctuation by having easy access anisotropy in the system. The other attitude is actually opposite. They're saying, let the fluctuation be, and let's exploit the fluctuation in those easy plane anisotropy system or even isotropic system. So along the first way of fighting against the fluctuations, the goal is to really maintain the magnetic order that was originally there in the 3D counterpart. Over the years, it has been shown success in realizing or stabilizing ferromagnetism, antiferromagnetism, and helimagnetism in the 2D element due to the anisotropy. In this second route, where people exploit the fluctuations, the goal was to promote new magnetic states that were given due to the strong fluctuations. So there have been predictions about spin-induced vestigial states or spin vortex, anti-vortex pairs, and so on and so forth. So in the other aspect about twisting engineering, so far there has been both experimental and theoretical establishment of realizing new magnetic phases. Examples include non-collinear spin textures or topological magnetism or even topological magnons. So my group at the University of Michigan, we are trying to study all these three aspects of 2D magnetism. Like many groups have been done, we also focused a lot on fight against the fluctuations to stabilize the magnetic orders. Our effort has been focused in both chrome triodide and chrome sulfide bromide. So building on our understanding on the chrome triodide, we also made twisted chrome triodide systems and trying to leverage this twist degree of freedom to realize non-collinear spins in twisted chrome triodide system. So that's another aspect we have been focusing on. So for this third aspect here, that is to utilizing fluctuations, it's more of our recent effort. And we are going to focus on this effort in this particular talk. Okay, so let me by saying that when we talk about orders, temperature is one way to tune the fluctuations in the system and tune the system to go through fully ordered state to an intermediate state and then to a fully disordered state. This kind of intermediate state is often present in many phase transitions. People often refer it as short-range ordered phase state. Okay. So in addition to temperature, we also have other orthogonal ways to tune the fluctuations. For example, we can reduce the dimensionality to increase the fluctuation. We can also increase disorder in the system to increase the fluctuation. And just similar like temperature, we will also have this sort of like three segments along this axis. So if we connect this phase diagram together, we will have the so-called intermediate regime that is sitting between the fully ordered regime and the fully disordered regime. So then what's so special about this intermediate regime, right? If it's just a sort of like less interesting short-range ordered state, it may not be so surprising and exciting. But there is a special case that is the so-called vestigial order, which is described by distinct symmetries of this state as compared to the fully ordered and fully disordered states. So because we often classify phases matter based on symmetry, if this regime actually have its own symmetry characters, then it is justified to say itself is a unique phase of matter here. Okay. If we use the order parameter language, we can see that in this fully ordered regime, the primary order parameter eta is present. Simultaneously, the quadratic combination or even higher order combinations of the order parameter are present. So then this fully ordered state has the lowest symmetry across this phase diagram. When we enter into this so-called vestigial order, the primary order parameter eta is actually absent due to the fluctuation. However, this quadratic combination of the order parameter or higher order combinations, they are not zero. And more importantly, these non-zero higher order combinations actually has broken symmetries as compared to the disordered phase. So that's why it's so special for this blue, this yellow regime it is. Yeah. So this regime will have slightly higher symmetry than the fully ordered state, but has lower symmetry than the fully disordered regime. In the fully disordered regime, it's just our familiar case where nothing is present. Okay. So then the material platform that we use to explore this physics is nickel phosphorus trisulfide. So we are going to give some basics about its structure and magnetism that was known from the literature. And we are going to argue that the known knowledge actually support the possibility for such a system to host this vestigial state. Following that, we are going to briefly talk about our experimental technique, which is this magneto-Raman spectroscopy. So we are going to give a little bit of introduction about how a Raman spectroscopy detects different magnetic degree of freedom. And then we will show our result. By the end, I hope that I can convince you there's this phase diagram of 3 different regimes in this nickel phosphorus trisulfide system as functions of temperature and thickness. Okay, let's start by the first part. So for a 3D nickel phosphor trisulfide, structure-wise, the building block is this nickel sitting in the center of this octahedral formed by this sulfur atom. So then within the layer, meaning that in the plane, this kind of octahedral arranged in this honeycomb lattice that you can see. And this parallelogram highlights the unit cell of the honeycomb lattice. And then the phosphorus sitting in the center of the honeycomb lattice with 2 of them on top of each other to form a bipyramid structure. So then for this kind of layers, it will stack along the vertical direction to form the bulk. And its stacking is obeying the so-called monoclinic stacking, meaning that the honeycomb lattice shifts along the axis by 1/3 of the unit cell between adjacent layers. Okay, so that's for the crystal structure. So then we look at the spin state. So the nickel is at this 2+ valence state. And due to the octahedral crystal environment, the d orbital of nickel is split into Eg and T2G. And the 8 electrons of the nickel ion are arranged in such a way to end up into this S = 1 spin state. Okay. And then through the literature, we know that for the interlayer exchange coupling, it's complex here. So it contains it contains up to the 3rd nearest neighbor. So the first nearest neighbor is ferromagnetic coupling. The second is a weak antiferromagnetic coupling. And the third is a more stronger ferromagnetic coupling. So then in addition to that, we will also have anisotropy. The dominant anisotropy is this easy plane anisotropy. And then within the plane, you also have a very weak easy axis anisotropy that is along the x-axis direction. So then between the layers, the magnetic interaction is ferromagnetic for both the nearest neighbor and next nearest neighbor. Okay. So then the whole spin Hamiltonian looks like this. So let's break it into parts and see its consequence. So the 3 intralayer exchange coupling will define this zigzag antiferromagnetic chain. It tells us that this kind of chain structure is going to come up. So then the interlayer exchange coupling here is going to tell you 2 things. The first thing is that the ferromagnetic nature is going to assure the chain arrangement between the 2 layers are exactly the same because of ferromagnetic coupling. And second, because of the next nearest neighboring coupling, that tells you about the coordinating environment that is monoclinic stacking. So it will assure that your chain direction is going to be along this monoclinic stack shift vector direction. Okay. So lastly, the anisotropy is going to define the spin direction itself. So the easy plane will tell you that spin is going to be in the plane, and then the easy axis is going to force the spin to be aligned in the in-plane axis direction. So picture-wise, below the critical temperature of 155 Kelvin for 3D nickel phosphor trisulfide, the magnetic ground state is this kind of zigzag antiferromagnetic chains that is running within the plane and also across the layers. Okay. From the symmetry perspective, we notice here. So first, because of this chain chooses one of the three zigzag directions, so then it will break the threefold rotational symmetry of individual layers. So breaking of rotational symmetry is the first note here. Second, if you look at here, structure-wise, due to the honeycomb lattice, we will have two nickel sites per primitive cell. But this zigzag antiferromagnetic order will have 4 nickel sites per magnetic primitive cell. So then the magnetism actually breaks the translational symmetry, and it has a wave vector that equals to the momentum space endpoint momentum. Okay, so then we note that to say this zigzag antiferromagnetism also breaks translational symmetry with a wave vector of Km. M notes the endpoint in the momentum space. Okay, so then in the literature, people actually peel down the 3D nickel phosphor trisulfide down to 2D and try to understand how this magnetic order evolves as a function of thickness. The general conclusion thus far is that the zigzag antiferromagnetism survives down to the bilayer, but vanishes in monolayer nickel phosphor trisulfide through literatures here. So they are mainly told by different optical techniques. For example, Raman spectroscopy, they focus on this EG mode splitting. So you can see that the EG mode splitting survives all the way down to the bilayer and vanishes in monolayer. So this proves the broken threefold rotational symmetry. Okay. Another optical technique is a photoluminescence. There is an exceptionally sharp exciton peak for nickel phosphor trisulfide, and this peak broadens and shrinks in intensity as we go down to thinner and thinner layers. Because this photoluminescence is related with magnetism, so then people attribute to the fact that this magnetism also diminishes down to monolayer through this set of measurement. And again, PL is not sensitive to your null vector direction, right? So then they only tell whether you have zigzag chain or not, rather than they say whether you have null vector positive or negative. So then they are only sensitive to this threefold rotational symmetry. Another technique is a linear dichrism. It really measures rotational symmetry breaking directly. So you can also see that this linear dichrism signal is there down to the bilayer, but absent in monolayer. So then all these optical techniques, they all say the threefold rotational symmetry breaking signature extends all the way down to the bilayer, but not monolayer. But as we said before, this zigzag antiferromagnetism actually breaks both threefold rotational symmetry and also translational symmetry. By only seeing signatures that break threefold rotational symmetry, we cannot directly associate to the zigzag antiferromagnetism per se. We have to have experimental signature to also tell whether the translational symmetry behaves in the same way or not. Okay, so then this gives us the leadway for the system because it breaks two different of symmetries. In the zigzag antiferromagnetic state, it breaks both rotational symmetry and translational symmetry. This regime corresponds to this fully ordered regime that is marked blue in our diagram here. Then, in the paramagnetic regime, we will have no rotational symmetry breaking and no translational symmetry breaking. This is just bare lattice itself. This corresponds to our regime 3 in the phase diagram, the fully disordered regime. So then there can be an intermediate regime that we only have one symmetry that is breaking. Here is the breaking of the rotational symmetry but no translational symmetry breaking. This is actually the regime 2 in this diagram. So by saying this, I hope to convince you that nickel phosphor trisulfide has the ability of supporting this yellow regime where only one symmetry is breaking while the other is not. Okay. So then we use this experimental technique, magneto-Raman spectroscopy. So Raman spectroscopy is a light in, light out technique. The energy difference between the incoming and scattered light is due to the quasi-particles being scattered through this process. So then when we think about Raman spectroscopy, we can provide one way to think about it, which may not be rigorous enough, but it's very helpful in our understanding of Raman, especially for magneto-Ramans. So we are essentially detecting susceptibility, optical susceptibility in this process. And we know that the optical susceptibility is going to be changed by either order or excitations of the order. And when they are very small, we can treat them as Taylor expansions of those excitations to this susceptibility tensor. So if we assume there's no excitation, no order, then this is equilibrium state, so it's chi ij 0. But we can have this process that the light is scattered off by a phonon at wave vector. That wave vector equals to your static magnetic order's wave vector. So then this kind of combined scattering is a allowed process. And we often call it as a sort of like folded phonons. The phonon at finite wave vector being folded by the magnetic order to the gamma point and then become visible in the Raman process. Because of the participation of the magnetic order itself, this process actually is a way to detect your static magnetic order. So then Raman is possible to probe your magnetic order if it's at finite wave vector through this process. Another possibility is to probe the magnetic excitation at the gamma point. This is really just zone center single magnum process. And then another way is that we can do two spin excitation processes at the two opposite wave vectors. So then because of the two spin processes, then we can probe the spin fluctuations in this process as well as two magnum excitations sometimes. So then these are different ways for to see the magnetic information in a system through the Raman process. So our Raman spectroscopy setup is like this. We have this backscattering geometry. Incoming and scattered light are in the same side of the same side of the sample, and we can control the incident polarization and the scattered polarization to learn about symmetry information of the Raman tensor. And then we can use Bragg filter to get down to the lowest Raman shift to be 3 to 5 wave numbers, which is rather low and helpful for us to learn about low energy excitations. And temperature range is from 10 Kelvin up to room temperature. And we can apply magnetic field in both polar geometry and void geometry up to 7 Tesla. Polar is a field normal to the sample surface. Void is a field parallel to the sample surface. Okay, so then with those preparations, we can move to our result. So here we are showing the Raman spectra taking of the bulk nickel phosphorus trisulfide. So the two panels, the top one is for the room temperature data. The lower one is for the 10 Kelvin data. So for each panel, we will have two traces. The black one is for the parallel polarization channel, and the gray one is for the crossed polarization channel. So there are quite some features. Let's go by one. So the first feature is this very long tail that extends from the very low energy to about the 40 wave number-ish, and it only appears at high temperature. So this long tail is attributed to this quasi-elastic scattering that probes the spin fluctuation in the system that has been reported in literature here. The second feature are these EG modes. The EG modes splits when the zigzag chain forms. So this split of the EG mode probes the broken rotational symmetry, which has been reported in literature as well. The third one is this fully symmetric AG mode. It provides less information. Okay. And then you can see there's a teeny tiny weak peak here around 42 wave numbers. And this one is the single Magnum excitation at the gamma point. And this tells you a little bit about the Hamiltonian information. And it has been seen in literature last year too. So the last one is this weak peak around 30 wave number-ish. And this peak is actually not seen in the literature so far. And we attribute this peak to be a folded phonon with the wave vector at Km, that is the zigzag antiferromagnetism's wave vector. And because it is a folded phonon, it is sensitive to the breaking translational symmetry. Okay. In this talk, we focus on three features. The first feature is this quasi-elastic scattering because it's sensitive to spin fluctuations in the system. The second feature is this translational symmetry breaking signature mode, which is this folded phonon. And the third is this rotational symmetry breaking mode, which is this split of the EG phonon. Okay, let's start by the quasi-elastic scattering in the bulk nickel phosphide trisulfide. So this is a raw spectrum taken at 295 Kelvin. So then for every spectrum, we are going to integrate its spectral weight from 5 wave numbers all the way up to 40 wave numbers. And then it will give me one data point for one temperature. And then we do a temperature dependence of this kind of quasi-elastic scattering. So then here we are showing the data that is between 200 Kelvin and 10 Kelvin. So you will see two features here. So the first feature is that there is this kind of teeny tiny bump around 155 Kelvin. So this coincides with the literature assigned nail temperature for the bulk nickel phosphide trisulfide. This kind of teeny tiny peak signifies the critical spin fluctuation when this critical temperature sets in. Later on, we can see that the fluctuation keeps on decreasing, and up to a temperature, the fluctuation vanishes. So then the temperature at which the fluctuation vanishes, we note it as the suppressed QES temperature. That is around 90 Kelvin. This is to say that the spin fluctuation is suppressed to a level that is below our experimental technique, below this temperature. But however, it tells us that it's kind of interesting. Between the assigned critical temperature and this spin fluctuation suppression temperature, there is actually a fairly wide temperature range. This is actually not so common in many magnets with this kind of separation between spin fluctuation suppression temperature versus the ordering temperature. So this actually motivated us to ask how strong the fluctuation is in such a system, and how does this fluctuation extend in thinner layers. Okay. So then here is what we do. So we do the same plot for bulk, as for bulk for this 13 nanometer flake, and then for 4 layer, for 3 layer, for 2 layer. As you can see that as our thickness go thinner and thinner, the two things that we mentioned in the above in the page before actually changes. So this kind of suppression of quasi-elastic scattering temperature, it goes down gradually. So you can see that it started around 90, sorry, this arrow is shifting, 90 Kelvin-ish, goes down to about 50 Kelvin in 13 nanometer. And then actually it's no longer present in 4 layer, 3 layer, and 2 layer. Or in the other word, it's to say that in 4 layer, 3 layer, and 2 layer, this kind of fluctuation extends all the way down to our lowest temperature, 10 Kelvin. You can see this shaded blue background extends all the way down to the lowest temperature. So this is one feature. The second feature is that this teeny tiny bump that is there in the bulk became very broad and take up a much bigger spectral weight in this kind of few layer cases. So these two things tells us that the spin fluctuations in the few layer cases survives down to the lowest temperature, and also the critical fluctuation takes a way higher spectral weight around the 100-ish temperature. Okay, so after this, we decide to look at the translational symmetry breaking and rotational symmetry breaking signatures and see how do they evolve as function of temperature and also dimensionality. Here we are showing the data still for the bulk nickel phosphor trisulfide. So this is a raw spectrum in the top panel. And then in the lower panel are just color map of the temperature dependent Raman spectra for both modes. So what you can see is that, for the rotational symmetry breaking feature, you can see that it starts at one single mode at high temperature, splits into two modes. That's where the rotational symmetry is noted. And this critical temperature is around 155 Kelvin, close to the nail temperature assigned in the literature. Okay, but then for this translational symmetry breaking mode, it was absent all the way down to about 90 Kelvin. And this 90 Kelvin was actually close to the spin fluctuation suppression temperature that we said before, right? So then we can do a careful fit of this temperature dependent data here. So we can fit the intensity of this translational symmetry breaking mode as a function of temperature, and also the frequency split of this EG split mode as a function of temperature as well, and put them together with this quasi-elastic scattering's temperature dependence. So then we can see, as we said just now, this rotational symmetry breaking mode onset at this so-called literature's nail temperature. And then this translational symmetry breaking mode onset at the temperature where the spin fluctuation is quenched. So then we note that, so above this 155 Kelvin, no symmetry is breaking. So that is just our paramagnetic phase. Between 155 and this 90 Kelvin, it's only the rotational symmetry is breaking, but the translational symmetry didn't break over this regime. So then it's more fair to say that this TN3D is actually the vestigial order's onset temperature rather than the AFM's onset temperature, because translational symmetry didn't break at this temperature. Translational symmetry breaks at this lower 90 Kelvin temperature. So then below this 90 Kelvin, both translational symmetry and rotational symmetry are breaking. So then this is the zigzag antiferromagnetic ground state for the 3D nickel phosphorus trisulfide. So then this is to say in the bulk, we actually, along the temperature axis, we actually have these three different regimes already. Okay, so then we also take a look at the thickness dependence of these two symmetry breaking signatures. For the translational symmetry breaking mode, you can see that it became broader and broader and then vanishes below 12 layers. And then for this rotational symmetry breaking mode, they are present all the way down to the 2 layer, just the same way as literature been said. We can also fit this mode characteristics as a function of thickness. They are here. For the rotational symmetry breaking one, the frequency split is nearly constant all the way down to the bilayer. The line width of the mode only gets big in the bilayer. It's a sudden increase of the line modes into the bilayer. But nonetheless, this rotational symmetry breaking signature extends all the way down to the bilayer. In contrast to this is the translational symmetry breaking mode. So you can see that the line widths actually diverge around 10 nanometer-ish, while the intensity also gets down to 0 around 10 nanometer-ish. Here, we purposely plot the relative ratio between the intensity of translational mode, breaking mode, and rotational symmetry breaking mode, in case people may worry, is it possible that it's just our sensitivity gets weaker in the few layers? So that's why we don't see the translational symmetry breaking mode in thin layers. This kind of a relative plot assures us that, no, it is really the translational symmetry breaking mode vanishes way quicker than the rotational symmetry breaking mode. Yeah. So this is sort of like a horizontal cut in this phase diagram at a fixed temperature and running across different thickness. Okay. So then we do a sort of like harder work because we want to construct the phase diagram. The harder work is that we do temperature dependent measurement for a few different thickness. So then for the bulk, we can clearly see we have the 3 regimes that are separated by the 2 temperature scales. in the 13 nanometer sample, we also have 3 regimes, but then we can see that the FM temperature actually got much lower. It shrinks from 90 Kelvin to 50 Kelvin, 90 Kelvin in the bulk to 50 Kelvin in this 13 nanometer sample. And then down to the 4 layer, we actually no longer have this FM critical temperature. Even if it were there, it has to be lower than our lowest temperature of 10 Kelvin here. Okay. So then we can construct such a phase diagram. So horizontal axis is a thickness, vertical axis is a temperature. So then for the bulk sample, and the thickness all the way down to 10 nanometer, we can realize all the 3 regimes, the paramagnetism regime, the vestigial regime, and the zigzag antiferromagnetism regime. But then for the samples that are thinner than 10 nanometer and all the way down to bilayer, we only see 2 regimes, which is the paramagnetic regime and also the vestigial regime. So this is the same as our sort of like phase diagram where we motivated with at the beginning. Okay. So then the last part I want to say is that it's a vestigial state, but it's a so-called Z3 post-nematic state. The reason is because it has 3 discrete rotational symmetry breaking domain states. So let's see here. We illustrate this with a 4-layer nickel phosphorus trisulfide system. In 4-layer, we've already known that there's no antiferromagnetism. There's only this vestigial state that breaks the rotational symmetry. So then we can use this experimental technique, linear dichrism, that is very sensitive to rotational symmetry breaking, but it's more efficient in taking a map as compared to Raman spectroscopy. So we do this kind of measurement over this sample area. You can see that where the dashed line circles is our 4-layer regime. It divides into 3 different regimes, like sort of whitish regime, and then the more red regime, and the intermediate regime. So this 3 regime has different intensity of linear dichrism. So then we can park into individual regime and plot the polarization dependence of the linear dichrism. Okay, so then we can see that indeed we have 3 different orientation of the polarization dependence in this 3 regime. And their orientation difference are 120 degrees from each other. So then these are the 3 discrete domain states for this vestigial order. And we also verify with Raman spectroscopy that the EG mode split. So you can also see there are 3 different possibilities that are rotated by 120 degrees. Okay, they correspond to the 3 ways that the zigzag chain can run across. Okay, so with this, I'm summarizing this talk. So I hope that through this talk, I convince you that we discovered this Z3 post-nematic state in this 2D limit by leveraging the spin fluctuation. It is actually a positive demonstration of spin fluctuation can give you something that is interesting and useful rather than just destroying things. Okay, there are still many open questions. So we want to ask, how do those magnetic excitations behave as we go to thinner layers and as we enter into different regimes of this phase diagram? And we can also ask whether we can do some kind of external control to manipulate across the nematicity and antiferromagnetism transitions. And we can also ask whether there are other systems where the spin fluctuation can give interesting vestigial states. Maybe there are also many other questions that we can brainstorm after this first demonstration. So finally, I just want to thank the team who made this work possible. The work is carried out by my postdoc, Zeliang Sun. And then the collaboration has been done in terms of theory with Kai Sun at Michigan and DFT calculation with Liuyan at Washington University, St. Louis, and Monte Carlo calculation with Ziang. And then transmission electron microscopy measurement were in collaboration with Professor Robert Houghton at Michigan, and magnetoraman spectroscopy were in close collaboration with Professor Rui He at Texas Tech. And the single crystal nickel phosphorus trisulfide is from Professor David Mandre's group. And with that, thank you so much for your time and attention.
Thank you. Any questions? Hello. Thank you for a very beautiful talk. I have a question about that zone folded phonon. Do you know which irrap that phonon belongs to? Is it coming from the acoustic branch or?
We think it's coming from the acoustic branch in collaboration with our DFT calculation person. It's because like all the optical branch are at higher frequencies than this 30 wave number. So then there's no optical phonon that is at this much low frequency. And then when he look into the acoustic branch at the endpoint, it is close to this 30 wave number, although it's not exactly at the 30 wave number.
I see. And is it like a Raman irrap or IR irrap?
I believe it's Raman because it's Raman active here. Yeah. Yeah.
Okay. Yeah, I was just wondering, like in case like this kind of zone folding can allow for IR phonons to be visible in some ways in Raman spectroscopy.
I should check with him more carefully. Yeah.
Okay, thank you.
Could you please show the spin Hamiltonian you had at the very beginning?
Okay. It's here.
Yeah, I'm a little bit confused about the last term. Is the last term itself breaking threefold rotation symmetry? You said there was an easy axis along the x-axis?
Yeah, for the spin itself.
Right, so if you have a coupling to the lattice, then the rotational symmetry breaking is already explicitly broken by the Hamiltonian. It's not spontaneously broken.
Yeah, I think your concern perhaps it should be more about this interlayer stacking that breaks the rotational symmetry to start with, because eventually we are saying our spin is actually fluctuating in the thin layer. So then spins itself's direction is actually not a major sort of source of breaking rotational symmetry. It's more of the formation of the zigzag chain, which is formed by a fluctuating spin that breaks the rotational symmetry. But then people naturally would think, okay, your crystal structure already is in this monoclinic stacking, and somehow your coordination of your interlayer exchange coupling tells the system, at least tells the spin about the lattice monoclinicity. So then how do you know whether this is the source of breaking rotational symmetry or the formation of zigzag chain is a breaking of the rotational symmetry? That whole question, that is actually the question our reviewer asked us. So we agree that this is a concern, meaning that our system, the rotational symmetry breaking in a single crystal is not spontaneous because of the interlayer coupling. Yeah, but then the question would be that how strong this so-called pinion field is. If it's a strong pinion field, then what we would expect would be, let me show you the temperature dependence of this. Yeah, if it's a very strong pinion field, then this sort of like a split of the EG mode is not going to show up like this kind of autoparameter behavior. You will see a round corner. The stronger of the pinion field, the more round of this corner would be. Yeah. So in our case, given the data is showing this quite nice autoparameter kind of onset, I would say that the pinion field is present, but its impact to the physics is not as big. That's my understanding.
Okay, thank you.
Yeah. Okay, thank you so much.
Thank you very much.